Welcome everyone. In this video, we are going to use early quantum mechanics to derive a formula for energy levels of electrons in hydrogen-like atoms. What do I mean by hydrogen-like atoms? Let me show you. So, we will have an nucleus perhaps, a nucleus, and inside that nucleus there will be protons and neutrons. However, we're not interested in neutrons for now, so we will only be interested in protons. Let's say that we have the atomic number as Z. So this represents how many protons we have. If we have a helium atom, then we have 2 for Z. If we have a hydrogen atom, then we have 1 for Z, okay? And we put an E here. And this is going to be plus ZE. What does this mean? It means that E is the charge of an electron. And as you know, protons and electrons have the same charge. Only difference is they are oppositely charged. Protons are positive, that's where the positive comes from, and electrons are negative. And around this nucleus, there will be an orbit. Our electron will be orbiting this nucleus. And oh, that's looking very big. That shouldn't be that big. Electrons are very tiny. So we have an electron. And why did I say that this is an hydrogen-like atom? Here's the catch. Our derivation requires that there is only one electron. However, we don't care about the number of protons. For example, if we have an helium atom, it would have two protons, but if we have an ion of helium, well, then it can have an electron, okay? So we can even use lithium. In that case, we would need to have it positively 2 charged so that it will have only an electron left. If we have 1 electron, our calculations hold. So, as I said, we want to derive a formula for the energy levels of this electron. And you can already see why I call this early quantum mechanics, because in the modern quantum mechanics, we don't draw certain orbits. There is an probability cloud, right? That comes from the wave function of an electron. But here we have a certain orbit, and it is certain because I call this radius r. This is the radius of the orbit. And even though this is early quantum mechanics, the results are completely correct. And this calculation was first done by Niels Bohr. So enough said, let's get started. The electron will be orbiting in a circle. And why does it orbit? Well, because there is a force of attraction between the electron and between the proton. So how can we find that force of attraction? Well, we find it by using Coulomb's law. It says the force of attraction is going to be a constant, Coulomb's constant, times the charge of the first one, so ZE, the charge of the nucleus, times the charge of the second one. So we can put a times E or just E like this, E squared. Divided by the distance, divided by the square of the distance between them, so we have R squared. This is going to be the net force that acts on the electron. But what is the net force? How can we represent it in a better way? We could say it is mass times A from Newton's second law, and that would be completely correct. But we don't need to do this because we have a special formula for A here. This is a circular motion, so the acceleration is the centripetal acceleration. And for that, I derived a formula already in a previous video. You can find it from the cards right now, also from the descriptions part. And if we use that formula, we know that acceleration is going to be v squared divided by r. From this, I want to solve for v squared. If I do that, what do I see? Well, I see r's cancel, and if I divide both sides by m, I can get the equation that v squared is equal to k times z times e squared divided by mass times the radius. Okay, and by the way, I forgot to say it at the beginning, but this is a long derivation for a video, so in this video we will only find r in terms of other quantities, and then in a future video, in the following video, we will find V, and then we will combine them all to find the energy states. Okay, so for this video, we only want to find R. What is R? That's the question. And here comes the quantum part. I mean, up to this point, this was all classical mechanics. There isn't any quantum things going on, but now there is. We will say, okay, we know that particles are both waves and particles. So if this is the circle that the electron is going around, then its wave function is going to be wrapped around it, like, right? It is traveling around as well. And we say there should be a specific way that this is wrapped around. Because remember this, electron is going infinitely many times nearly. It is going so fast and it is going around all the time. So if there is a little shift in the wave function, if it comes here and it doesn't complete to a full circle, if perhaps shifts a little, well then, since there are many times that the electron orbits, there will be destructive interference and the wave function will be gone. It will be cancelled, and if there is no wave function, there is no particle. And that is not the case, clearly. So here comes the important idea. If we have the circumference of the circle, which is 2 pi r, this should be equal to a, very important, an integer multiple of the wavelength of the electron. The lambda here is the wavelength, and n is an element of the integers, actually positive integers. Okay, here is the important part, as I said. And why is this correct? Well, as I said, if this is not n, if this is not an integer, then there will be destructive interference. This n avoids that. So this n avoids destructive interference. Okay, this is very important, and this might be a tricky idea, I know. So if you have any concerns about this, please write that in the comment section and I will try to answer all of your questions. So we got this, and now we will use something that is called de Broglie's hypothesis. So what does de Broglie tell us, who is a scientist at the time, a physicist? De Broglie. Now, de Broglie tells us lambda wavelength can be represented as, it is equal to h divided by p. What is h? H is called Planck's constant. What is p? P is the momentum. So we can represent it as h divided by, momentum is defined as mass times the velocity. Okay, this comes from de Broglie's hypothesis. There isn't really a proof for this. This is just a hypothesis, and it works out very good. It works out just fine. So we got this. And what do I want to do now? Well, I want to substitute for lambda here. Okay, so let's do that. Let's do it with black again. Let's do it with black. We have 2 pi r is equal to n, but instead of lambda this time, I am going to write h divided by mass times the velocity, and this part comes from de Broglie's hypothesis. So thank you very much, de Broglie. And okay, how does this help us? How does this help us? Well, look at this. We have velocity here, and we have a formula for velocity squared, speed squared here. So maybe we can combine them two, and then they can be simplified, and we will be left with r in terms of mass, z, k, pi, that kind of quantities, okay? Pi is not a quantity, of course, it's just a number. So if I arrange this equation, I can get mvr. I just multiplied by mv and divide by 2 pi is equal to n times h divided by 2 pi. And this guy, h divided by 2 pi, appears a lot in lots of calculations. So scientists chose to give it a special symbol. We name it as n times h bar. This is also called reduced Planck constant because it is obviously less than Planck's constant since we divide by 2 pi, which is greater than 1. So this is just the definition of h bar, okay? It is h divided by 2 pi. Here, I will actually continue on a new page. So we have mvr is equal to n times h bar. Now, if I square both sides, what will happen? We will get m squared, v squared, r squared is equal to n squared and h bar squared. All great. And here, I can solve for v squared. Oh, look at this. I can solve for v squared. What is v squared? It is going to be equal to n squared h squared divided by m squared and r squared. But you might be asking, why did you solve for v squared? I solved for v squared because we already have a formula for it. So we can equalize these two formulas. And if we do that, we will get v. So we have this formula, and it is also equal to the formula that we derived at the beginning, which is kz e squared divided by mass times the radius. Alright, and now look at this. We have r, and anything else is just constant. Mass is constant, Planck's constant is constant, and k, z, e, everything is constant. Just r is left, so we can solve for the radius of the orbit. And let's do that. First, we see that one m cancels here and another r cancels here. And as a result, we are left with n squared h bar squared divided by mr is equal to k z e squared. And if I solve this equation for r, which you can do yourself, I will basically divide by this and multiply by mr and then divide by m as well. I will get, let's see, n squared h bar squared divided by mkze squared. Let's see, is this correct? We have this at the top. Yep, this is correct. So this is the formula for r, the radius. And oftentimes we put a subscript n here because n is the only thing that can change in this formula. I mean, it is a constant. Yeah, it is a number, but it could be 1, 2, 3. It is just a positive number and can change. However, h bar, mass of the electron, k, Coulomb's constant, z, e squared, they can't change, okay? And obviously, actually, z could change as well. If we have a hydrogen, helium or lithium, it changes. But as I said, oftentimes we write an n here to show the different energy levels, different radius levels actually for our electron as n changes. So this is it for this video. In a future video, that is, I guess, will be uploaded in the next couple of days, we will derive a formula for v in terms of the quantities that you see right now for r, in terms of n, k, and other stuff, and then we will combine these two so that we will finally have a formula for E n. What is this? This is the main question. Anyways, I hope you enjoyed this video and learned something. If you have any questions, please add them in the comment section. I hope to see you in another video. Until then, take care.